So we're talking about units, and we're going to talk about the metric system and the metric prefixes. We will be using scientific notation a lot. So if you need a review of scientific notation, Appendix 1A will give you that review. If you need help remembering how to do scientific notation, I'll be happy to help you during lab, but I'm not going to lecture on that, okay? So we're going to go straight to the metric prefixes. So these prefixes, which are on that list of things you're supposed to memorize, are all multiples of 10. And that's what the metric system is based on, is everything is just a multiple of 10. So the multiplier, the prefix, just changes the size of the unit. We need units of different sizes because it's more convenient that way. If I'm going to measure the distance between Reedley and Fresno City College, I'm not going to do it in inches or even feet. What unit would I use? Miles. Because that gives me a reasonable number of miles. We like to use a unit that is similar in size to what we're measuring. In the metric system, we can make any size unit that we need by putting a multiplier in front of it. So, kilometer, it's meter with the prefix kilo in front of it. Kilo means 1,000 or 10 to the third. So 1 kilometer is 1,000 meters or 10 to the third meters. If we think about, let's say milli. So the prefix milli, anybody know what that means? 10 to the what? 10 to the negative 3. So 1 millimeter equals 1 times 10 to the minus third meters. Do you see what's going on here? This is the prefix milli. Over here, I wrote what it means. I like to put a 1 times in front of it because now this number is in scientific notation, and so then when we put it into our calculators, we don't have to worry, I was supposed to use the 10 to the x button, or what the heck am I doing with that? Okay. The prefix micro. Micro means 10 to the minus 6. So what if instead of meters, I'm using liters? 1 microliter equals 1 times 10 to the minus 6 liters. The prefix symbol is like a nickname for this power of 10. There are other ways to write these conversion factors, and if you're good with the metric system, I'm not going to correct you or change it. But I'm going to use this method in lecture to be consistent. You put the prefix on one side, and you put the 10 to the something that it means on the other side. It works every single time. Okay? So these are the metric prefixes and their meanings. These are not all of them. And we don't need all of them for chemistry. I'll tell you mega, kilo, centi, milli, micro, nano. You know, if the number of prefixes on that list are just too much for you, these are the ones that are the most important. You might not be able to pass the quiz just knowing these, but you'll be able to get through the class pretty well just knowing these, because the rest of them are only going to come up occasionally. The multiplier here with all the zeros, it makes a nice pattern, doesn't it? That's not very helpful to memorize, right? So that's there, but just skip over. This is what you should memorize. 10 to the what? So most of these exponents are multiples of 3, if that helps you at all. So here we've got 3, 6, 9, 12, 15, 18. And here we have minus 3, minus 6, minus 9, etc. And it's just these guys in the middle that are a little bit off from that. But most of the time it's a multiple of 3. And that's just, you got to memorize it. The symbols, you got to be careful with the capitalization. We've got capital M, we've got lowercase m, and we've got a Greek m, mu. You'll see that after kilo, all of the rest of them are capitals. The capital letter tends to make the unit larger. A megameter is 1,000,000 meters. And the small letter ones tend to make things smaller. Kilo is the one exception to that. I don't know why. So we should be able to do things like this. How long is 4.5 megameters in meters? So there's different ways that you can do this. So 4.5 megameters. What does the prefix mega stand for? Mega equals 10 to the what? 10 to the 6th. So what if I just rewrote that with the meaning in there? What if I wrote 4.5 times and then 10 to the 6th instead of mega? That is one way that you can convert with the metric system. You don't always end up with your number in proper scientific notation, but many times that doesn't matter, and you can fix that later. So that's a very fast way to convert. Where that prefix is, I just insert the meaning of it, 10 to the whatever. Here's kind of the opposite sort of a question. 7.13 times 10 to the minus 9 liters is equivalent to how many nanoliters? Well, what does the prefix nano mean? 10 to the what? Sounds like nano. 9. It's 10 to the minus 9. Oh, look. That is 10 to the minus 9. So what we can do is just take this part, this times 10 to the minus 9, and write nano for that. So this is equal to 7.13 nanoliters. So that's kind of a shortcut, cheaty way of doing these conversions. It's not always convenient. So we're also going to look at dimensional analysis and crossing out units. That way always works. Any questions about this slide? So we talked about units for length and mass and time and temperature. Volume and density are what are called derived units. So a derived unit is a combination of other units. So the metric system and the SI system have a set of base units. All other units are combinations of those units. So for a rate of speed, for a car on the highway, we usually measure that in miles per hour. So that's a combination of two units. That's a derived unit. Or we can do it in meters per second. We don't do a lot with speed in chemistry because we don't throw things across the room too much. But we do a lot of things with volume. Volume is a measure of three-dimensional space. So if you take a regular three-dimensional, like that one, but not there yet. So if you take a cube, right, it's got a length and a width and a height. And we know from geometry that the volume of the cube is the length times the width times the height. Well, if we measure this height in meters and the length in meters and the width in meters and we multiply them, we get meters cubed as the unit. So any unit of length cubed is going to be a volume unit. Becomes a unit volume. There's a word missing. A unit of volume, or it should be volume unit. Okay? So that's a derived unit. Other common volume units in chemistry are the liter, which has the abbreviation capital L, or the milliliter. What does milli mean? 10 to the minus 3. So this is equal to 10 to the minus 3 liters. If you're a little rusty on your exponents and stuff, if we have a negative exponent here, that's the same as 1 over 10 to the third. So a milliliter is 1/1000th of a liter. So if we want to make a large cube that measures 10 centimeters on a side, how many little cubes that are 1 centimeter on a side do we need? Well, to get 10 centimeters on a side, we'd have to have 10 of those cubes, right? And along this side, we'd need 10, and going up, we'd need 10, right? So if we have a 10 centimeter cube, that's a cube that's 10 centimeters on a side, that's going to take 1,000 of the little 1 centimeter cubes. It's not 10 of them, it's 10 times 10 times 10. Length times width times height. We have relationships between different units. We often need to convert between the metric system and the English system. Most of these conversion factors are not ones that you need to memorize. Is it on here? Yeah. Okay, so this one, 1 inch equals 2.54 centimeters. You should memorize that one. We use that one a lot, and you should memorize that one. The other one you should know, which is one of those things that's so simple that we forget about it. 1 cubic centimeter is the same as 1 milliliter. And in medicine they call it a cc, a cubic centimeter. So that's the same size. The rest of these, if you need to do these conversions, you're just going to go look them up in a table. I would give you a table on an exam, or the conversion factors would be provided for you. Okay, so don't worry about memorizing the exact relationship between a kilogram and pounds or anything like that. Density is also a derived unit. Density is the mass of a substance or a sample divided by its volume. So we can write it out in words, or we can use letter abbreviations, D equals M over V. That's an equation that you need to know. So common units for liquids and solids for density would be grams per milliliter or grams per cubic centimeter. That's going to give us reasonable numbers. The density might be 0.8 grams per milliliter or 11.4 grams per cubic centimeter. Reasonable numbers. For gases, though, we tend to express their densities in grams per liter because gases are so much less dense. Density is a physical property that does depend on temperature. Which of these do you think changes with temperature, the mass or the volume? The volume. Mass is not affected by temperature, but the volume is. It's not significant, it's not huge for liquids and solids, but liquids and solids do tend to expand slightly as they get larger. So you'll often see a density specified at a particular temperature. So this table shows densities at 20 degrees Celsius. So, well, what if you're working with it at 25 degrees Celsius? Is that going to throw everything off? No. But if you're working at 100 or minus 50, then you probably need to consider the temperatures. So over here we have listed for several different common substances. And you'll notice for water, they specify the density of ice, which is solid water, and liquid water. So the density of ice at 0 degrees Celsius, which is at the freezing point, is 0.917 grams per cubic centimeter. Water reaches its maximum density at 4 degrees Celsius. So the density of water is 1.00 at 4 degrees Celsius. And that would be a good one to know. Does that seem awfully nice that water has a density of 1? It seems like, you go to the grocery store and your bill comes out to 100.00. Exactly $100, and you're like, what? Maybe I should go buy a lottery ticket today. It's just like weird number karma day or something. This isn't a coincidence. The way the metric system units were set up, they were done in a way to make the density of water be exactly 1. And you see that these are listed in order of increasing density. Platinum up here is one of the most dense elements, 21.4 grams per cubic centimeter. And again, other than water being 1, which should be easy enough to remember, you do not need to memorize those other densities. There's no point. I don't know all of them, except I do remember mercury. I'm not sure why, but probably because I've used it so much. But you don't need to memorize those. We talked about chemical and physical properties. We can also categorize properties as being intensive or extensive. So an intensive property does not depend on the amount of substance. It is intrinsic to the substances. No matter how big your sample is, an intensive property will always be the same. And we can use intensive properties to identify what the substance is. So these sorts of properties include density. The density of a substance does not change with the amount of substance. If you have a big bar of iron, what's iron's density? 7.86. It'll have a density of 7.86. If you cut it in half, each piece will have a density of 7.86. Yes, you changed the size of the sample, but its mass and its volume changed by the same factor, and so its density remains the same. The melting point. Ice melts at 0 degrees Celsius. Doesn't matter if you have 1 ice cube or a glacier. The melting point's the same. Color. You take a piece of candy and it's red and you cut it in half. It's still red. It doesn't depend on the amount of substance. Those intensive properties are intrinsic to that substance. Extensive property does depend on the amount of substance. So mass, length, volume are all extensive properties. I take that piece of candy and I cut it in half. Its mass changes. Its volume changes. Its length changes. Okay, intensive versus extensive. Any questions?
What is the extensive properties? What are they used for?
Well,
intensive is for identifying.
We can use intensive to identify. Extensive would just pertain to an individual sample. It can't be used to identify something. It's just this other category of properties. Okay, so let's do this example, calculating density. Some of these have stories which may or may not make them more interesting. This one's a little bit interesting. A man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? This is one way you can identify the metal that a thing is made out of. Now, a ring is a little different than a cube, right? You can't just measure length times width times height. Rings often have, kind of different contours and things, and it's hard to come up with a way to measure the volume just using rulers and geometry. So displacement is where you would take a graduated cylinder would be the most useful. Take a graduated cylinder and put some water in it and make a note of the level. When you put the ring in it, it's going to displace some of the water and cause the water level to rise, right? If you fill the bathtub half full and then you get into the bathtub, the water level goes up, right? Because your body displaces it. That's why you don't want to fill the bathtub all the way to the top before you get in, because you're going to make a big mess. So the difference in the water levels gives us the volume of the object, and that's a very convenient way to find the volume of an irregularly shaped object. So we're asked to calculate, well, we're not asked to calculate the density. We're asked to figure out, is the ring made of platinum? Well, what numbers are we given in here? We're given 3.15 grams, and we're given 0.233 cubic centimeters. One of the things that students struggle with in this class is these word problems and critical thinking skills. And so I'm going to do my best to help you learn how to solve problems like this. The first thing is read the problem all the way through. And then a next step, if you're not sure exactly what to do when you've done that, go through, pull out the numbers. The numbers are probably going to be important. And then let's identify what they are. So 3.15 grams, we know that gram is a unit of mass. It also tells us here that this is the mass of the ring. So that's the mass of the ring. Here it says it displaces this much water. It doesn't specifically say that that's the volume, but cubic centimeter is a unit of volume, and displacement is a technique for measuring volume. So this is the volume. So hopefully we remember that density can be used to identify a substance. So we have the mass and the volume. We could calculate the density. Maybe we should do that. So density is mass divided by volume. So we're going to take the mass, 3.15 grams, divide by the volume. I brought my calculator today. And so this equals 13.5 grams per cubic centimeter. Does that immediately tell us whether it's platinum or not? Only if we happen to know the density of platinum off the top of our heads. So let's go back here and look. Come on, pointer. Yes. I don't know what's up with that. Down there, you can see it. The platinum density is 21.4. The density we calculated is closer to the density of mercury. Could you make a ring out of mercury? No, it's a liquid at room temperature. But if its density matches mercury, how could it not be mercury? It could be hollow, but let's say it's not hollow. Mixture of other metals. So if we took something lighter, like aluminum, and mixed it with platinum, it may have some platinum in it, but it may be partly aluminum. So the density of something helps us to identify, but it's not always conclusive. So is the ring platinum?
No.
No, it's not.
So the question about how the ring displays so that amount of water. So anytime you place anything into an amount of water, the displacement accounts for
the volume
of that object.
of the object.
Okay.
Now that's assuming that the object is more dense than water so that it actually sinks.
Yeah.
If it floats, that's not going to work as well.
Then it wouldn't.
It would
displace the water.
it would give you the volume of that part of the object that's below the surface of the water,
Oh, okay.
but not the part that's above.
Okay.
Yeah. So is the ring made of platinum? No. That's going to cause a discussion, isn't it? Okay, here's the next question. The woman in this example is shocked that the ring is fake and returns it. She buys a new ring that has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is the new ring platinum? Did she finally get what she was paying for? Well, since we just did a problem like this, we should, be able to do this one a little easier. Oh, well, we need the density. Density is mass over volume. I want you to practice showing your work. I know that some problems like this you could just do on your calculator and write the answer down. Practice showing your work on simple problems. So you write the equation. You put the values into the equation. 4.53 grams. You always write the unit. So there I have my equation with the numbers in it. I do the math. And I write down the answer, 21.4. That's a weird looking 21. Let's try that again. 21.4. And the units, they don't cancel out or anything, so you just write all of them in there. Grams per cubic centimeter. So 21.4, let's go back and check the density because our short-term memories are not so great. Oh, 21.4. What if the measured density was 21.3? It's probably still platinum. Measurements are not perfect, and we'll be talking about that. Any questions?